The Millennium Falcon weaving through a tumbling field of boulders is the most scientifically dishonest 10 seconds in cinema history. Rocks the size of office buildings, spinning and colliding, filling every inch of the frame. Han Solo yanking the controls, C-3PO announcing the odds, the ship barely squeezing through gaps that close like teeth. It's one of the most iconic sequences in science fiction. It's also almost completely wrong, and the problem isn't just that Hollywood lied to us, the problem is that the lie stuck, deeply, to the point where mission planners still have to explain to journalists why crossing the asteroid belt isn't the most dangerous part of going to the outer solar system, because the real danger is something far quieter, far less cinematic, and far more difficult to survive. The asteroid belt occupies a region of space between Mars and Jupiter, a band roughly 140 million miles wide. When you say that out loud, it sounds dense. It sounds like a wall. Scientists estimate there are somewhere between 1 and 2 million asteroids in that belt larger than a kilometer across, and countless smaller fragments. If you've never thought hard about what that actually means spatially, your brain probably conjures something like a crowded room, objects pressing against each other, jostling for space. The reality is almost the opposite. If you took every single asteroid in the belt and pressed them all together, the combined mass would be less than 4% of the Moon. The average distance between any two objects large enough to see is measured in hundreds of thousands of miles. The belt isn't a wall, it isn't even a crowd. It's a vast, cold, nearly empty corridor of space, punctuated by the occasional lonely rock drifting in darkness. We know this because we've sent spacecraft through it, multiple times. Pioneer 10 crossed the asteroid belt in 1972 and emerged without a scratch. Voyager 1, Voyager 2, New Horizons, Galileo, Cassini, all of them passed through without a single significant collision. Mission planners didn't plot white-knuckle routes through narrow gaps. They aimed their probes and let them fly. The asteroid belt, statistically speaking, is one of the least threatening regions of the inner solar system for an unmanned spacecraft. If you were on a ship traveling through it, you might not see a single asteroid during the entire crossing. Space is that empty. And yet, there are no safe routes through the asteroid belt. Not for us, not for human beings, not with anything we currently have, or anything we're likely to build in the next several decades. Not because of the rocks, because of everything else. The first problem is one that never makes it into science fiction. Micrometeorites, not the kilometer-wide boulders that Hollywood loves, the tiny ones. Fragments the size of a grain of sand, a pebble, a marble. Objects so small they're invisible to every detection system we have, traveling at speeds between 10 and 70 kilometers per second. At those velocities, a particle smaller than a pencil tip carries the kinetic energy of a small explosive. It punches through metal, it doesn't announce itself. It doesn't appear on radar, it simply arrives, and then the damage is done. The asteroid belt increases the density of this debris compared to open interplanetary space, not dramatically, not catastrophically for a probe, but a crewed spacecraft isn't a probe. It has life support systems, fuel lines, pressure vessels, crew compartments. A micrometeorite strike in the wrong place doesn't just damage equipment, it starts a cascade. Then there's radiation. Deep space beyond the protection of Earth's magnetic field is a fundamentally different radiation environment than anything human beings evolved to handle. Two sources dominate. The first is solar energetic particles, high-speed charged particles launched by solar flares and coronal mass ejections. The second is galactic cosmic rays, ultra-high energy particles streaming in from outside the solar system, accelerated by dying stars and the remnants of ancient supernovae. These aren't like X-rays at a hospital. They penetrate aluminum, they penetrate water, they tear through DNA like a bullet through paper, leaving behind broken strands, misread genetic code, and cells that either die or mutate. A round trip to Jupiter, which requires crossing the belt twice and spending months in deep space, would expose a crew member to radiation doses that exceed NASA's current lifetime limits. And current limits already come with a meaningfully elevated cancer risk. You don't feel it happening. There's no alarm, no warning light. Your cells are being restructured on the molecular level, and your body has no mechanism to tell you. But it's not just radiation. The human body wasn't designed for zero gravity, and what happens to it in prolonged microgravity reads less like a medical report and more like a slow dismantling. Bone density drops at roughly 1 to 2% per month in the spine and hip, the load-bearing structures your SL. Keelton built specifically to fight gravity. After 6 months, an astronaut's bones resemble those of a person decades older. After a year-long transit to the outer solar system, the loss becomes structural, a fracture risk that doesn't just affect performance in space, it follows you home if you ever get there. Meanwhile, muscles that exist only to resist gravity begin to waste. Your heart, which is a muscle, shrinks. It doesn't need to pump blood upward against gravity anymore, so it adapts efficiently and lethally by becoming smaller and weaker. Fluid that normally pools in your legs redistributes upward, pressing against your optic nerves, slowly flattening your eyeballs, degrading your vision in ways that may not fully reverse. Astronauts returning from 6-month stays on the International Space Station, which is still well within Earth's magnetic field and gravitational influence, require months of rehabilitation to walk normally. A transit to the outer solar system would take far longer. The body that arrives at the destination would not be the same body that left. And here is where the cascade begins. A crew member weakened by bone loss and cardiovascular deterioration is also the crew member responsible for repairing life support systems. A radiation-damaged immune system is less capable of fighting off bacteria and viruses that quietly thrive inside spacecraft, mutating in microgravity into more aggressive strains. A crew experiencing visual impairment is operating navigation systems and monitoring instrument panels that require precise sight. Psychological deterioration from isolation, confinement, and the absence of natural light cycles adds cognitive impairment and interpersonal conflict to a closed system where both are potentially fatal. Communication delay between the asteroid belt and Earth runs to 20 minutes one way at peak distance. A fire, a pressure leak, a medical emergency. By the time mission control receives your distress signal and sends a response, 40 minutes have passed. You solved it yourself, or you didn't solve it. There are no redundancies sufficient to cover every failure mode simultaneously. Every system on a crewed spacecraft depends on every other system. Power generation feeds life support. Life support maintains the pressure environment that keeps crew functional. Crew functionality maintains every repair and operational decision that keeps the spacecraft intact. Remove one piece and the structure doesn't weaken, it begins to collapse. The asteroid belt transit isn't a single danger to navigate. It's a months-long accumulation of low-probability events, each manageable in isolation, compounding in reality into something that current technology and current human biology cannot reliably survive, let alone survive intact. This is the honest answer to the title. Not that the asteroid belt will smash your ship, it almost certainly won't. The rocks are too far apart, the math is too generous. What the belt represents is a waypoint in a journey that is, with everything we currently possess, too long, too exposed, and too demanding for a human being to endure and return from. In functional health. The danger isn't a specific obstacle, it's duration, it's exposure, it's the accumulated weight of a universe that was not built with human fragility in mind. We dream of the outer solar system, and there are reasons worth honoring in that dream. But between us and Jupiter, and Saturn, and everything beyond, lies not a wall of rock, but something quieter and harder to defeat. The simple, relentless physics of what space does to a living body, given enough time. Every probe we've sent past the belt crossed it without incident. Pioneer 10 is still out there, billions of miles away, long silent, having completed a journey no human crew has attempted. Those spacecraft crossed the belt because they had no biology to protect, no immune systems to compromise, no bones to hollow out. They are extensions of human curiosity without human limitation, and maybe that's the more honest version of deep space exploration for now. Not us, but our instruments, not our hands, but our mathematics. We built machines capable of crossing the outer solar system precisely because we understood, even if we rarely admit it, that we cannot do it ourselves. That understanding isn't defeat, it's the most human thing about the whole endeavor. We looked at a place we could not go, and we found a way to see it anyway.